Good morning, students. Hello, students. Okay, I'll start with the lecture. So it started in the electromagnetic theory 2, the chapter 1, steady current and then magnetic field. And we started with what is called as Biot-Savart's law. The Biot-Savart law gives the expression for magnetic field due to element means very small part of the wire carrying a current, and from this the field of the element one can find the field of the wire. Huh? No problem. No. Right. No problem. And using this Biot-Savart's law, we have found the expression for magnetic field due to the straight wire, then magnetic field due to the coil, the magnetic field at a point on the axis of a coil, and from that we found the magnetic field due to Helmholtz coil and the solenoid. So this was done using the Biot-Savart's law. Now, for the straight wire or a coil or a solenoid, comparatively it is easy to calculate the field. But for the circuits of irregular shape, there is a difficulty in calculating the magnetic field because what involves is an integral. Evaluation of the integral becomes a issue there. So Biot-Savart law has a limitation. Then there is another law called as Amperes Circuital Law. Amperes Circuital Law, and we are stating this Amperes Circuital Law, and we'll see how to apply this to find the magnetic field, and we'll find it also for a straight wire, and we'll find that comparatively it is very simple than that using the Biot-Savart's law. So the Amperes Circuital Law again has a limitation. It can be applied to the symmetric circuits, but one can easily calculate the magnetic field. Now, let us recall what you have done in the electromagnetic theory 1 in the first term in the electrostatics. In the electrostatics, what was there is the electric field. In magnetism, we have a magnetic field. Then electrostatics, we had started with the Coulomb's law. The Coulomb's law was giving the expression for the force, and from the force one could find the electric field, expression for the electric field. Then using the Coulomb's law, we can easily find the electric field due to the point charge, electric field due to the two charges. But as the number of the charges increases, then calculation of the electric field becomes difficult, because electric field is a vector quantity. It becomes very difficult to calculate the or add the vectors, many vectors. There is a problem there. Then also for other charge distribution, what comes there is the evaluation of the integral, so it becomes little difficult. And then from that, Coulomb's law, which was used to find out electric field, we started with what is called the Gauss's law. See, we use the Gauss's law. Now, Coulomb's law is similar to the Biot-Savart's law. Coulomb's law in electrostatics is similar to Biot-Savart's law in the magnetism. Similarly, the Gauss's law in the electrostatic, similar to that, we have Amperes Circuital Law in the magnetism. And we had seen that using the Coulomb's Gauss's law, one can easily calculate the electric field. Very simple. And mathematically, the form of the equation for the Amperes Circuital Law and the Gauss's law is similar. Form is similar, but meaning is different. The Gauss's law, you can find out electric field. Amperes Circuital Law, you can find out the magnetic field. So the form of the equation is this. So we will try to recall what is called as a Gauss's law. See, for the Gauss's law, there are some charges are there. So let us say charge Q is there, or it may be set of the charges or distribution of the charges. I'm just taking the simple example. The charge is Q, but there can be a set of the charges or a distribution of the charges. Then to apply, you can find out at any point P, you can find out the electric field. You can find it in Coulomb's law. With the help of the Gauss's law, you can find out in much easier way. So what is required is, to apply the Gauss's law, we require a closed surface. So around that charge, we take a closed surface, closed surface. We choose the closed surface enclosing that charge, and at the point P where you are finding the electric field should be on the closed surface. Then, according to the Gauss's law, the flux over this closed surface is equal to 1 upon epsilon 0. Epsilon 0 is permittivity into charge which is enclosed. Now, where is the charge? It doesn't matter. How much is the charge? Doesn't matter. Whether it is a point charge or a charge distribution, it doesn't matter. What is important is that charge should be inside that closed surface. So this is Gauss's law. The flux over the closed surface equal to 1 upon epsilon 0 times the charge is enclosed. Now this is electric flux. See, this is the electric flux. Now electric flux is nothing but electric field into the area. Here surface area of this closed surface. And if the surface is not uniform, then we take the integral. We take an integral. It is a closed surface and it is electric field dot element area. So there is a flux. So this turns out to be 1 upon epsilon 0 times Q. So we can write this flux as electric field into the area. So basically this is Gauss's law in electrostatics in the integral form. We call it as a integral form. The Gauss's law in the integral form. Now, in comparison with it, we'll see what is that law in the magnetism. That law is called as the Amperes Circuital Law. So first we will see only mathematical form. So here, in this case, instead of 1 upon epsilon 0, what here is mu naught. And I had mentioned this. Most of the equations in the electrostatic magnetostatics, you can get equation magnetostatic from the electrostatic by replacing epsilon 0 by 1 by mu naught. Epsilon 0 is the permittivity of the free space, mu naught is the permeability. So you replace 1 by epsilon 0 by mu naught. So you can replace it. Now here, the charge, see charge enclosed by the surface, we replace it by current. We will see the meaning of that. Because the magnetism is produced by the electricity, so we take a current. Then, instead of the surface integral, we take the line integral. So it is a line integral. C is written. C means path. It is a line integral. So instead of electric field, we have magnetic field. Dot dl. Since it's line integral, that length element comes. Dot vector dl. So from the equation in the electrostatic, Gauss's law, we can write Amperes Circuital Law in the magnetism. So what is to be done is replace 1 upon epsilon 0 by mu naught, charge by current, and the surface integral by line integral, and the E by B. And again, since here is the line integral, what comes is dl. So now this is the, as far as the mathematics is concerned, this is the form of that Amperes Circuital Law. And in the words, see line integral of a magnetic field, see line integral of the magnetic field along the closed path. See closed path, where in the Coulomb's law it is a closed surface area. Here is closed path, that means length is equal to mu naught times the total current crossing the closed path. Now let us see the meaning of this. Now suppose you have wire like this. Wire is there carrying a current. Wire is there carrying a current. Just like in electrostatic, you have the charge. So here, a wire is there carrying a current. Because of the current, there is electric field. So there is a magnetic field. So there is a magnetic field here. Because of the current, there is a magnetic field at this point. Let us say this point is P, magnetic field. Just like because of the charge, there is an electric field. There is electric field. Then, just like in electrostatic, you choose the closed surface around that charge. Now, in this case, you choose the closed path around that current. So we choose the chose path. So here, a path is chosen, closed path is chosen. In the electrostatic, we are choosing the closed surface. Now, this closed path should be chosen in such a way that when you choose the closed path, that point where you find the magnetic field lies on that closed path. So this is that closed path we have chosen. Closed path we have chosen around that wire, and that so that we choose the closed path in such a way that point where you are finding the magnetic field lies on that path. Just like in the electrostatic, the point where you are finding the magnetic field was lying on the closed surface. Then, see now we know that whenever there is a current, around it there is a magnetic field in the form of a closed loop. Wire carrying a current produces a magnetic field around it, and there are circular loop around that wire and concentric loop. So now what will happen here is, at this point, the magnetic field will be tangential to that closed path. Magnetic field will be tangential to that closed path, because field lines will lie in this plane. Then, see, we choose an element of this closed path. So here what is chosen is the element, this element of the closed, just like we have chosen the area element of that closed surface. So in Amperes Circuital Law, we choose the element of that closed path. Then the line integral, so we find BDL. So line means we are adding it all over the closed path. So line integral of vector B dot dl is equal to mu naught times that current enclosed. It is given that total current crossing the path. Here what happened is, see this closed path which is there, see current is crossing once. Suppose we are like this. Suppose we are like this. So current is crossing twice. Then you have to take I equal to 2I. Suppose it is crossing only once, you have to take it I. If it is crossing twice, it is 2I. If it is crossing thrice, then it will be 3I. So this is how we take that current. So this current is a current which is crossing that closed path. So remember that this closed path is a imaginary path. It is an imaginary closed path. It is called the Amperian loop. Just like in the Gauss's law, that closed surface is the is the imaginary surface. That was called as a Gaussian surface. So here, this closed path chosen is called as a Amperian path. So now this is the meaning of this Amperes Circuital Law. It is similar to the Gauss's law. So when you are studying this Amperes Circuital Law, just try to recall the Gauss's law. Right? So this is a statement. This is a line integral. See, this is a circle is there. So it is a loop integral. Vector B dot dl equal to mu naught I E. I is that current is crossing. So not a single current. The current may cross that path many times. So accordingly that times you have to take it. Now this is Amperes Circuital Law in the integral form. Because integral is there. But remember that in the Gauss's theorem, this quantity is a flux. But this quantity is not a flux. Integral B dl is not a flux. So there is no physical quantity corresponding to integral of B dl. So in electrostatic, it represents the flux, but here it is not representing the flux. So that you have to keep in mind. Now this is in the integral form. So it is the integral form like this. So just like we have done it in the electrostatics, that Gauss's law we had written in differential form. So first it was written in integral form, then in differential form. So here also we will try to write the Amperes Circuital Law in the differential form. So now current. See, we define the quantity called as the electric current density. Electric current density means suppose wire is there, then current divided by area of the cross section. See, this density is nothing but current. See, current divided by area of the cross section. That's called the current density. Now the wire may not be uniform, so we write the integral. So this J is the current density. See, current density into the area. That means current divided by area into area is a current. That is how it is written. This IE is a current. J is a current density. Current divided by area. So that ds is also area. So area cancel. So what you get is a current. So that I suffix C is written as surface integral. It is surface integral. Vector J dot n cap ds. Because vector ds, we write it as magnitude ds into the unit vector. And unit vector of area is n cap. So we write substitute first here IE like this. Then on this left, this is the left hand side. See, on the left hand side, we now apply Curl theorem. So we will recall the Curl theorem. What is the Curl theorem? The line integral becomes the surface integral. So remember that in Curl theorem, is used to change the line integral to surface integral or surface integral to line integral. So line integral, surface integral. Actually, what we do is there is a surface, and we choose the path around it. So it is a plane surface, open surface. So this is the surface. This is the surface, and this periphery of that surface is that length, closed loop. So the surface, the open surface, this is called the open surface, not closed surface. Open surface, it is surrounded by a periphery, border. Alright? So this is that closed path, that periphery is a closed path. So that's why we are using here the loop integral, because this path C is closed. So line integral is contained in surface integral. Then this function, B is a function. the function becomes curl of the function. Say, the line integral becomes surface integral, the function becomes curl of the function. Now for line integral, element is dl. For surface integral, element is vector ds. And vector ds is written as that unit vector into the magnitude. So this we have written. Okay. Now, other side is written as it is. This is written as it is here. Then see, now here what happened is, why we have used this curl theorem in order to have surface integral on both the sides, because in this equation there is a surface integral on the right hand side, line integral on the left hand side. So in order to write the surface on the both the sides, we have converted that curl this line integral into surface integral by using the curl theorem. And because of that, if these are two surface integrals, so integrand, these are integrands. Integrands are equal. Integrands are equal means here that nds is there on this side, nds is on this side, and on this side what is there is curl of b, and on the other side it will integrand will be mu naught and j. So mu naught j. So curl of b equal to mu naught j. Now this is called as a differential form of the Amperes Circuital Law. So we have stated Amperes Circuital Law is the integral form. We convert it into the differential form. Same thing was done in the Gauss's theorem. We had written in the integral form, then we had expressed that in terms of the differential form by using a curl theorem only. Then we go further, we get something more from this. See, this is the equation 1 which we have found, differential form. Curl of b equal to mu naught j is a differential form of the Amperes Circuital Law. Then what you do is, for this equation 1, take a divergence. Divergence means del dot. Curl means del cross. See, the curl means del cross. Divergence means del dot. On the both the sides, you take del dot. Both the sides you take del dot. Then, see here, what happens is del dot del cross b. So we call it the divergence of the curl. Del dot means divergence, del cross means curl. So divergence of the curl. And in the first term, we have proved this property, and we have used it many times, that divergence of the curl is equal to 0. See, this is a property, divergence of the curl equal to 0. So now this left hand side becomes 0. Mu naught is constant, it comes outside. So mu naught cannot be equal to 0, because mu naught equal to 4 pi into 10 raised to minus 7. It has some value, it cannot be equal to 0. So del dot j equal to 0. Now this is called the continuity equation for the steady current. Continuity equation for the steady current. The current is always continuous. Okay. So a constant steady current, constant current. And basically what happens here is, in ordinary language, del means derivative. Derivative of the current will be equal to 0 when the current is constant. This is written in more technical language, but basically del means, this del means derivative, and derivative of that current will be equal to 0 when the current is constant, so steady current. So sometimes it is called as steady state condition. Okay, then here, as I mentioned earlier, even in these electrostatics, why the Gauss's law was used? Because it was easier to apply. But only it has a limitation. You can apply only to the symmetric cases. But using the Gauss's law, one can easily find electric field than by using the Coulomb's law. In same way here, using the Amperes Circuital Law, you can easily find out the magnetic field than using the Biot-Savart's law. And we'll take that example and see. We use the Biot-Savart's law for a straight wire. The derivation was lengthy, almost running into 2 pages. And we'll see that for a same straight wire, when it is applied, Amperes Circuital Law, you can get a magnetic field in few steps. And that's what we are going to see next. So magnetic field due to the infinitely long, the straight wire. So we have straight wire here. So this is a straight wire. It is a magnified diagram is drawn. The current is flowing. See, current is flowing. So current is flowing, and to apply the Amperes circuital law, we require a closed path and enclosing that current. So current should cross that path. So we choose the circle. We choose the circle here. See, this is a circle we choose. This we choose. Concentric circle around that wire. This circle we have chosen. Now this circle here, now in this case, is a closed path. We have chosen some closed path. It happens to be a this field line. It happens to be field line, but actually here we are choosing Ampere loop. It is called Ampere loop, a closed path. Then here what we find is we take the element this DL element DL, very small part. Then this it subtend the angle d theta. The distance r you have to find a magnetic field. You are finding magnetic field at a point P, at distance r. R is the radius of that Amperean loop. Then we know that, see, this Amperean loop with loop we have chosen, it turns out to be a magnetic field line. It is forming the closed loop. And for a magnetic field line, magnetic field is tangent to that. So this is the magnetic field tangent to that. This is a tangent to that. Magnetic field tangent to that. Okay. So again, what happens is the magnetic field is at same distance. See, every point on this loop is same distance from the wire. So magnetic field will be same there. It will be same. It is a constant. At the same distance, magnetic field will be same. Now, what we do is we take this Amperes circuital law. We will apply the Amperes circuital law. So here mu naught is there. It will continue. Then through this loop, the current is crossing only once. So we have written I. Suppose it was crossing twice, we will have written 2I. So this I is written. Then this BDL. See, the DL, that element will be tangential to that loop, and magnetic field is also tangential. So angle between B and DL is 0. So we have written B dot DL, A dot B is AB cos theta. So theta is 0. Theta is 0. Because here the direction of DL and direction of B coincides. So I just written B just to show that it is a tangential. B suffix C, DL cos 0. Then here DL, we are integrating this DL, and DL, you have to take the DL all around that loop, That means that angle theta will go from 0 to, so it will go from 0 to 360 degrees. Because what happened is, at each and every point that element will be there. So when you are adding the magnetic field, you have to take each and every DL. So that angle d theta will go from 0 to 360 degrees, that means 2 pi. So limit here is 0 to 2 pi. Then DL equals S equal to R theta, DL equal to R d theta. So that DL equal to R d theta. Then B and R comes out as a constant. Then integral of d theta is theta. These are 2 pi is upper limit, 0 is the lower limit. So upper limit minus lower limit. Substitute upper limit. Theta equal to 2 pi minus theta equal to 0. So what we get is 2 pi. So it turns out to be B 2 pi R. Other side is mu naught I. So B equal to mu naught I divided by 2 pi R. This is the formula. Same formula we have derived using Biot-Savart's law. But that derivation was running into almost 2 pages. Here, in fact, you can get in only in 2 steps. Write this Amperes circuital law and substitute there and integrate. In 3 steps, you will get this expression for magnetic field. So it is so easy. So Amperes circuital law is we can easily find out the magnetic field, but only in a certain. You should be able to get the loop of this type. Here, the loop is symmetric. So if you are able to get a symmetric loop, then you can easily find out the magnetic field. So you can apply the magnetic field in such situations. Then see the magnetic flux. I will define here magnetic flux. See, magnetic flux definition is same as that of the electric flux. Magnetic field into area. See, magnetic field into area. suppose that here what happens is magnetic field over the area. See, normally we choose a plane surface like this. The current is flowing through that. When the current is flowing through that, then the field lines are produced. And in some area we choose, through that, how much magnetic field is crossing, how many lines are passing. That is given by B dot n ds. Actually, B dot vector ds. Vector ds is written as n cap ds. So this is the basic formula for the flux. The definition of the flux, magnetic flux is similar to that of the electric flux. Only instead of E, we have B. Otherwise, it is same. Remember, the integral BdL is not a magnetic flux. Integral BdS, vector ds, is a magnetic flux. Then we use here Gauss divergence theorem. Gauss's divergence theorem. In Gauss's divergence theorem, surface integral becomes the volume integral. See, if you want to have a volume integral from surface integral, use a Gauss's divergence theorem. And the function, B is a function, become divergence of the function. So B becomes del dot B, divergence. And since surface integral here ds is there, volume integral here dv is there. Okay, so that is the Gauss's law. Then, see, for the closed surface, the flux enters as well as leaves the, see, the magnetic field lines, suppose magnetic field line, they always from the closed loop. So if you choose any closed surface, it will enter the loop and it will enter the surface and leave the surface. The flux entering is same as flux leaving. Flux entering is negative, flux leaving is positive. So total flux is 0. So the total flux is 0. But what is the definition of flux? The surface integral of B dot n ds. What is it? Then you convert into volume integral, you get like this. And now integral is 0, that means integrand is 0. So del dot B equal to 0. Now this del dot B equal to 0, this is called as the Gauss's law in the magnetostatics. See, Gauss's law in the magnetostatic, del dot B equal to 0. In electrostatic, del dot B is not equal to 0. It will have some value. So here del dot B, instead del dot B there it was the rho. Here del dot E equal to rho. Here del dot B equal to 0. So this is a Gauss's law of the magnetostatic. So remember this, del dot B equal to 0. Then we find next is one more we take the magnetic field. See, magnetic field due to the long coaxial cable. Now what is a coaxial cable? You might have studied in your lower class, maybe first year or second year, maybe second year in electricity. Coaxial cable, especially for the cable TVs, that cable is a coaxial. See, the mostly this for the TVs, that cable, even the wire from the antenna, this dish to the TV is not, see, normally what happens when you say wire, electrical wire, there are two wires like this. DC current enters and current leaves. Two wires we take. Okay? But there is a problem with this pair of the wire. One line and other neutral, or one positive, other negative. There is a problem with that. So as far as magnetic field is concerned, there is a problem. There is a radiation, in fact. Energy is lost. So if it carries a signal, signal means radio signal, then the signal will be lost because there is a radiation. Now, instead of this pair of wires, what is used is, see, there is a center wire. There is a center wire. You might have seen this if you have cut the cable and seen of your cable TV or a dish antenna. At center there is a wire. So this wire, a center wire, here I have drawn it like this. Radius is A. Center actually it is very thin. I have drawn here is very broad. Actually it is very thin. And then you will find around that it is coated with the insulator, normally white in color. Coated with the insulator. It is coated with the insulator. Insulator is there. Then over this insulator you will find a wires like this, strands of wires. So when it is arranged around that insulator, it will form a cylinder. So we call it a metallic cylinder. So this is a central wire. So this is a central wire. In fact, this is a metallic cylinder. So one connection is to the central wire, other is the metallic cylinder. Now this metallic cylinder is made of the wires like this, wires. So that's why it is called the cable. It is not a continuous metallic piece, but the cylinder is made by keeping the wires around that insulator. Okay. So current may enter here and current may leave here. So current may enters to the center wire and it may leave through the cylinder, or it may enter the cylinder or leave through the center wire. So this is called the coaxial cable, and you can find that outside magnetic field is zero. By using your right hand thumb rule, you can find out. Outside magnetic field is zero. This you might have seen in the when you studied in your lower class. Outside magnetic field is zero. Because magnetic field is zero, the radiation is not there. Then inside the wire, again magnetic field is zero. Magnetic field is zero means what? The radiation is not there. Radiation will not be there. So magnetic field will be there only in this region. Region from the wire to this cylinder, the magnetic field will be there. So for a radius greater than A and less than B, the magnetic field will be there. And that also, by using the right hand thumb rule, you can show that the magnetic field is due to only central wire and not to the wire in the cylinder. The theory behind this you might have seen in the current electricity. And the field is there, see field is there here is only because of this central wire. And central wire is single wire. That means a straight wire. And for straight wire, it is mu naught I divided by 2 pi r. But you can, this r is can be only greater than A or less than B. Because outside this B, you cannot use this because the field becomes zero. Inside the wire also field is zero. So field is there only in this region. Okay, and that is due to the central wire, which is mu naught I divided by 2 pi. This is what we have derived. It is mu naught I divided by 2 pi r. Okay, and here also outside that wire, outside the cable, the field is zero. Because suppose you take another way of looking at it is, if you take a closed path around this, then through the central wire current may enter, through the cylinder current may leave. So the current is entering in that closed path and leaving the closed path. So direction opposite. So I minus I equal to 0. So that's why the magnetic field is 0. So that is the advantage of the coaxial cable. So that radiation loss is not there because magnetic field is 0. So this is the about the Amperes Circuital Law and its application. So I'll stop here and continue. Tomorrow is a public holiday. I'll continue day after tomorrow. Thank you very much.
Thank you, sir.